Hello, this is your friendly neighborhood ergonomics instructor, and today we're going to talk about chapter 3 in the book, Anthropometry. And to that, we shall get started. All right, there we go. Get my face out of the way. Again, this is chapter 3 in the book, and it's called Anthropometry. And what it is a measurement of the physical attributes of humans. Humans. That's what we're dealing with here, right? Over time, the body dimensions of the population changes. It does. People have become taller and heavier all the time. So I'm not short, I'm just on the right time, that's all. Used by manufacturers of consumer goods such as clothing, appliances, cars. I mean, if you're gonna make some clothing, it has to fit somebody, right? And how you just can't make it without any idea what you're doing. And that word comes from the Greek anthro, which is man, like anthropology, the study of mankind. Pometry, measure. So again, another Greek combination there. And in ergonomics, we use as a base for setting up a workstation, say a driver's area, an airline cockpit, and that type of thing. You just don't pull this stuff out of the sky. You have to have some reason for how big you're making it, how far the controls are, and that type of thing. There you go. There's a classic example of a guy that doesn't fit. I guess he's a pretty big guy in a pretty little car. So they don't make the cars for guys that big, the little cars anyhow. I'm sure a big pickup truck he might fit, but so anyhow, the basis for anthropometry is a careful measurement of human body dimensions of a set population. Height, weight, reach, both horizontal and vertical, stoop, grip strength, even circumferential measurements, and limb length, how long your arms are, how long your legs are, a lot of measurements. Need to answer the following questions. Does a person fit in a workplace? Is this person going to fit in this workplace? Or if one worker fits, do all workers fit? Of course, it's really just the workplace fit the worker, but that's what they're getting at. So if all workers do not fit, are some more likely to experience fatigue, injury, or diminished work performance due to a poor fit into a workplace. You can see that gentleman in that sports car, if he had to drive that thing for 8 hours a day, he's probably not going to be in pretty good shape, not very good shape when he's done. So there you go. 8'3" is the world's tallest living person. Now, when they build doorways, and that doorway he just came through, they don't build it for the world's tallest living person. Could you imagine that doorway would have to be almost a foot high, not just that doorway, but every doorway in the United States. That would be a lot of ways just to fit one guy. So he's just going to have to duck. That's all there is to it. If you're that tall, and you're going to have to duck because they're not going to build doorways to accommodate you. Now, if you had your home custom built, that'd be different. But 8'3", that's tall. It's essential to be aware of the potential effects, both positive and negative, that work design issues can have on both worker performance and fatigue. When designing or modifying equipment or work areas, the following factors need to be considered. Safe clearances or heights, for example, like doorways and walkways. Safe reach distance, for example, for equipment controls. Code requirements, what are the regulations are, we deal with those too. Safety features, for example, machine guards. Workstation design for workflow. So you got to accommodate the workflow as well. And that's what a person looks like to a person who studies anthropometry. Whoops. They just look like a whole bunch of different numbers, measurements. So how would the design of an automobile differ from that of a space capsule? What are the differences there? Well, if you design it on a mobile seat and cockpit, so to speak, you want to sell that automobile to a lot of people. So you're probably going to make it to try to cover a wide range of people. And of course, you have a big advantage in a car. You can make that seat adjustable. So that helps somewhat. It's somewhat adjustable. But in a space capsule, they're going to have to say, no, we're only going to put people in the space capsule that are from this height to this height. And the seat's probably not going to be adjustable, probably going to be built for you, I'm sure. Adjustability means extra parts, things can go wrong, and that's what they want in a space capsule. And in a space capsule, you have the controls that have to be within your reach, and there's a bunch of them. So they would design be quite a bit different, because in your space capsule, you're probably going to start with, if not a person, at least, okay, we're going to only get people from this height to this height with this region, etc. So you couldn't divide it, just make a space capsule and then get that 8'3" guy to try to fit into it. That would make no sense whatsoever. Oops, wrong way. How would the design of an office chair differ from that of a movie theater seat? Okay, again, they both want to have a lot of people use their products, right? And so an office chair is going to be used, though, for probably 8 hours a day. That's a lot different than a movie theater seat. Office chair, you really don't want your people falling asleep in it. Where a movie theater seat, some people probably do. And so that's a difference. And the office chair has to be mobile somewhat. So that kind of restricts what you can do weight-wise and everything else. And then the office chair, well, probably more so than the movie theater, the cost of each one has to be taken into consideration too. I'm sure in the movie theater too. But the office chair just has a lot of different things to it. Needs, like I said, it has to be able to move around, and you don't want it too comfortable. So then the movie theater seat. These are things that anthropometrists think of. Anthropometric tables are on 25 to 48 in the textbook. Now that's a lot of pages of a lot of numbers, and I don't expect you to go through them all and look at all that stuff, but to give you an idea of how much data is there. And we're going to look at the table 3.1 on page 25, which is simply height in inches for males age 20 and over. The percentile indicates that X% of the population has the same value or less than that value for a given measurement. Therefore, 100 minus X of the population has a value higher than X. So where do you fit, and does it make sense to you? So this is what it looks like right here. All racial and ethnic groups, they're 20 years and older. Number examined, the whole ring was 5,647 people. Well, I shouldn't say people. These are just males. And the mean 69.3. What's 69.3? 5'9" and a third inches, right? And if you go down to my group at 70 to 79, it's 68.2. So you can see that people my age are an inch shorter than the average even. And if you go to the 20 to 29, 69.4, that still an inch and a half, almost an inch and a quarter shorter than somebody, the average person aged 20 to 29. And then you look at the percentiles. So I'm like 5'6", that's 66 inches, and 79. So the percentile there is for my 25th percentile, be 66.3. So in other words, 1/4 of the people would be shorter than me, and 3/4 taller than me of my age group. Now I'm not comparing to anybody else in that particular case. So you can see all the numbers in here, and sometimes these numbers are only different by 1/10 of a foot. That's just a little bit more than an inch. An inch would be 1/12 of a foot. So, but that could mean a big difference when you're doing controls in something. So, and this is the graph. This is a symmetrical graph, or commonly called a bell curve, and it shows again the height of people and the average. And the graph itself tails off at either end because fewer people are extremely tall or extremely short. To the left of the average, there's a point known as the 5th percentile. You can see it's marked on there. And to the right, there's one that's the 95th percentile. So, and again, we're only one person in 20 is taller than this height. So you need to know whether you're designing for all potential uses or just the ones above or below average dimensions. This depends on what it is that you're designing. For example, if you were designing a doorway using the height, shoulder width, hip width, etc., of an average person, then half the people using the doorway would either be taller than the average or half would be wider. Since the tallest people are not unless they're the widest, more than half the users would have to bend down or turn sideways to get through the doorway. Therefore, in this case, you would need to design using dimensions of the widest and tallest people to ensure that everyone could walk through normally. Deciding on whether to use the 50th, 50th, and 95th percentile value depends on what you are designing for and who you're designing for. So as you can see, anthropometry is used usually in the design stage. It's kind of too late after you already got it built. So usually anthropometry design, they design for a range. So the principle is you allow for adjustments in position, size, intensity, and duration of the product or the system to accommodate unexpected circumstances and maximize use. And the design you commonly use from the 5th percentile female to the 95th percentile male, which will accommodate 95% of a 50-50 mixed population. So they're taking from the shortest group of females to the tallest group of males, and that's going to get 95% of a mixed population. And let's face it, most products are for a mixed population. Car seats, desk heights, keyboard supports, footrests, all that type of stuff. You can design for the extreme, accommodate the largest percent of the population group where adjustability is not feasible. You can go the 95th to the 100th percentile. Design maximum levels. In the principal design, you do go for the 95 to 100% token. Examples: clearance in doorways, distance of control button to operator. Rule of thumb is designed so that the tall can fit and the small can reach. Yeah, that's probably easier said than done. But again, you want to design it so the tall can fit into it, but the small can also reach the things in it. So, and I'm going to leave you with this words of wisdom. So I guess I'll speak louder from now on. That's it. See you next time.